Thank you, everyone. It's a real honor to be here with Ron, whom I met for the first time about 15 minutes ago. He just came in straight from the airport to be here with us, so it's a real honor to have him here and talking to us about his work. We're going to switch gears. We're going to talk about extreme weather and how extreme weather is influencing and should be influencing businesses around the world. And I don't think I have to tell people in this crowd that Mother Nature has been on a rampage this year. Thinking back to this winter and the record-breaking snowfall in the Sierra Nevada, followed by flooding in Texas and New England, followed by heat waves in various places. The heat, I know you all here in Idaho have been suffering mightily, as have many of the western states. And all of these types of extreme weather are posing a huge risk to our infrastructure, to our society, to our ecosystems. And that's the kind of work that Ron has been doing, is trying to understand how these extreme events can be translated to risk that is useful, that organizations can actually use to change their behavior to hopefully put us on a better trajectory. And we know why these extreme events are increasing in their frequency, their intensity, their duration. We know it's because we're adding these heat-trapping gases to the atmosphere at an unprecedented rate. We know that this past year, which was a record-breaking global temperature, probably the warmest year we've seen in over 100,000 years. We know that that was boosted by El Nino. But now we also know there are other things happening in the climate system that are making these kinds of events even more likely. We just heard a lot about the oceans, but as we look at the oceans now, there are ocean heat waves all around the globe. And these are helping to fuel not only these heat waves, but also extreme storms, heavier precipitation events, and all kinds of other extreme events. So without further ado, I know Ron has a lot of information to impart, so please take it away, Ron.
Thank you, Jen. Thanks for a wonderful introduction. But, you know, I'm deeply honored to be following Sylvia Earle, a hero of mine. I can't tell you what it feels like, but so if I start fainting on stage, you'll know why. We don't price nature. We don't price what we use from nature. We don't know how to price it even, you know, particularly when you're thinking about the future. The future is inherently uncertain, radically uncertain. So whatever we think we know about pricing nature today is really probably not really valid as we go forward. But that's true for corporations. Every one of our markets, financial markets around the world, every company, every country is mispriced from a financial point of view. I hope to show that to you. I also hope to show you how it's actually possible to measure what you can do about it. So one of the most interesting things is we can actually see the future if you really look hard. What does it look like? And where can you find it? How can you uncover that data? Let me show you what it looks like. This will take you back to your MBA days or physics days. It looks like a distribution. It's not a number. And if you were a person who could get down into an atom and look at an electron, you wouldn't see that electron. You would see a probability distribution. You wouldn't see it. All you could say is where it might be. And that is the metaphor for how we look at a radical future. So this is a case of Boise in the future. And on the left is a gray distribution. That's the past. And by the way, pretty much every insurance company, every corporation and every market is priced by looking at the past. Now, there's a big difference when you look at the future. And this is a word you're going to get used to in my talk, stochastic. That means uncertain or deeply uncertain. Here's Dubai. And in gray is all of history in Dubai ever measured. And you notice it doesn't extend very far to the right. And a few weeks ago, Dubai was hit with about 124 millimeters of rain in 6 hours. Now that's more than it ever experienced, never mind in 6 hours. And the question was, could you have seen that? You certainly couldn't have forecast that. I don't believe you can forecast. But what you can do is you can capture it in a distribution. So you see that dot and that 2017? That distribution in red was produced a year before that event. We didn't forecast that there'd be 124 millimeters, but we capture it. And because it's a little tail, the tail's thin there, that's a low probability event, but high impact. And it's capturing those low probability and high impact events that we really need. So this is a hotel owned by the Marriott. This is something that's very interesting. Acapulco had never experienced anything more than a Category 4 hurricane. CAT models in insurance companies use historical information. And along comes this Cat 4, and the night before, it turns into a Cat 5 and destroys every hotel on the beachfront. So if you were an insurance company insuring those hotels, you might have lost a lot of money that day because you thought you knew what the worst risk was. And the past can be compared to a future. And now we're looking at Boise. I thought I'd do a lot on Boise just to be local. And you can see that, that the probability of exceeding 21 days of hot days in a year, which is our current number of hot days, is very little, you know. But if I were to say, what would that look like in the next 5 years, that's what's called a climatology. It's about 3 times more. It gets worse. What's the probability of exceeding 35 days of heat, which I think we're expecting in Boise? And that is, I skipped something there. That is really 1 in 3 versus today it's measured as 1 in 100 by your insurance company. So let me show you some sovereign risk pictures of Idaho. This is stolen from a new product that we've developed for measuring sovereign risk in 136 countries. So there's where the population of Idaho is. And here's the population, and you can see it's pretty concentrated around the south there in this crescent. But you know, when you overlay the generating facilities and all of the electricity facilities of Idaho, most of it's down in that crescent. Most of it's where the heat's going to get, where it's going to get really hot, and where fires are going to burn, and you know, you won't be able to generate as much electricity. So there's tremendous knock-on effects that one would experience. So here we've got just one other thing. What's the maximum temperature that you could experience? And you can see that the distribution for the future looks quite a lot more skewed to the right. That is, there's more probability of many more days with very high temperatures. So that's what you're seeing here is, once again, these dots are all simulations, and I'll show you how we do that. That's a graph of what we expect the number of hot days in Boise to look like. So it starts off with something like 20 hot days, just the beginning of this decade. And it's probably going to go up to something like 100 hot days. So that the climate of Boise will change quite radically. It's happening in Toronto as well. Fire risk, we've seen this in the States, but here's fire risk in Idaho. And you can see it's pretty red down at the bottom. And it's getting much redder. This is the impact of fire risk in brown on the right. And that's pretty high. So these graphs aren't just for fun or just to brag. They are actually what you need in order to mitigate those risks today. to understand how to mitigate it and to understand the cost benefit. We don't have infinite cash to mitigate those risks, so what should we do first? How do we know that this data is good? How do you know that future data is actually good? It's a kind of quandary, you know. You develop future data and it's in the future, so how can you prove that it's good? Well, one thing you can do is go back to every nasty event that's occurred in the world and see if you captured it before the event occurred. So this is 10 cities in Europe. The black dots were actually black swans. In June of 2022, you would never have believed London would have over 41.5 degrees centigrade or over 110 Fahrenheit for a few days. What happens then is the railways buckle, or they soften. You can't run trains. So that's a big, big event for England. We've done this around the world, and we find that the stochastic methods that we're using actually capture 97% of those risks. So I guess we've got good data. So how do we do this? We've built a digital twin of the Earth as opposed to the real one that we just saw. This is Gen AI's view of what the Earth could look like. Anyway, we cover this Earth with something like 100 petabytes of data. That's 100 billion megabytes of data, just to put it in perspective. And that data covers every point on the Earth's surface, including the oceans, for all the hazards that could occur in that location. And the big goal of this is to understand how those hazards, or combinations of them, could affect physical assets. Why is that interesting? Because one of the things that's not measured today is the physical nature of the companies we see on the stock exchange, the companies we invest in. We know a company just by its financial record. We don't know that it owns buildings on sea level locations around the world. We don't know that it's going to get hit by cyclones that are more strong, etc. So this is a big hole in banking today. There isn't a bank I have come across anywhere that has this data. They've never had to keep it. So they can't actually measure climate financial risk. So we take this digital twin, and it's taken us 4 years to build it, and we use it to actually do stuff. So here's the Marriott Hotel, for example, if you want to know what could happen to Marriott. Those are all the hotels. These are groups of those hotels. It's thousands of hotels, and it's all over the world. And somehow you need to understand the risk. And the risk of a physical asset is very different than the risk of a financial asset. A bond is a bond is a bond. Doesn't matter where you are. A building is not a building. It's not a building. It depends where you are. Here's Pune, and the biggest events that were ever measured for insurance purposes are around the hundreds, the 100 to 200 millimeters. There's an event with 500 millimeters, and so on. So I call this knowing your bets, which is as important as knowing your risk. The bets are what's in that long tail. So we've taken this digital twin and applied it to 80,000 companies, which make up 2,100 financial indices and have about 5 million material physical assets in about 1 million places around the world. And we now can generate reports. There are 5 of these reports outside. You can actually peruse them. Please don't steal them, because I'll send you one. This is my one and only set. But there's a little explainer next to it. So that's 80,000 companies measured with the digital twin on demand. So here's a real example. This is a company that owns generating facilities in Chile, solar generating facilities. So who would have thought that as temperatures rise, solar gets less efficient? And Chile is meant to get more dry and with more heat. Same here. So this is the loss. This measures the loss of that solar generating capability And you might ask, well, what can we do about it now? Well, if we spent this money in those time periods, we would avoid something like 200 plus million in losses with 30 million investment now. So that's what you can do with the digital twin. Banks are big silos. Every part of the silos in those banks, thanks Jenai for this picture, is subject to climate risk. And we can measure every one of those and price them properly. Residential mortgage loans. This is Australia. And these are 10 cities in Australia. And these are the houses in those cities. And the red is what we estimate they would lose in physical value. And the red here indicates what we think will happen to insurance policies. As we know, in the United States now, I think 17 states have lost almost all of their insurance. So I'm going to leave it at that, and I hope we'll have some time for questions.
Well, we don't have a lot, but yeah, we only have less than a minute for questions, but the one that's at the top of my list would be, how do you see your stochastic method, which is really at the core of what you've been doing and is different from maybe what others have done? How does that differ from how we've been projecting the future climate using what I would call the normal climate models, which are based on physical equations and parameterization, so relationships that we know exist in the physical world? Stochastic is a type of AI. I know AI is in the name of your company, and some people may not really understand how a stochastic system works and how you're able to incorporate that uncertainty and that variability in the future. You know, what variables really are you ingesting?
That's a really excellent question. So where do you think those distributions come from? They are the sum of 85 climate models from the best institutions in the world, with every experiment that has been run with them aggregated into distributions. It's a very scientific method for doing that. But the basic point is this, is if you're looking at the future, nothing is certain. And so every one of those models produces a number. It's like having a mad scientist guessing the future. And that'll never happen, that specific thing. But if you take the ensemble of those models and aggregate them appropriately into a distribution, you now have our world view of what could happen. And, you know, we only use that worldview until we find our next bit of information. The next scientific piece, you know, the Antarctic is now sitting on a bed of water. Yeah. So Antarctica might melt a lot quicker than we thought. And that will change our view in the models. Our models will get better. And then in the next period, we redo those. We do this monthly. So those are updated monthly, but it's in some sense, we're getting our arms around the future rather than forecasting it. Because forecasting is a loser's game. Currently, every major consultant and every major bank I know of uses the following method. They guess one path into the future. It's called an NGFS scenario. And they say, in 2020, this is what's going to happen. It's deterministic.
Right.
The GDP in Singapore will be 2.5. Good luck. Okay? So they do a few of those, and they call that stochastic, but it isn't. That's just what if. Right. It's like taking a spreadsheet and changing a number. Stochastic is really getting your arms around the future, modeling that, shaping it with the best science that you can get. So we use a lot of climate science to do that shaping.
Well, I know we're out of time, but I just want to ask one more quick one because it ties back into what Sylvia was talking about, and that is, can your stochastic models capture abrupt shifts or tipping points?
we hope they can, but what the best we can do is, because those tipping points are sometimes quite far out, I mean, the uncertainty is when they will occur and how badly will that happen. Well, how badly, I think we know. They'll go off a cliff.
Yeah, a cliff is
When is the question? So what do you do with that information? Yes, we can get a distribution for possibilities of when the North Atlantic current will shift, for example. The question is, what do we do about that? And that is when you're dealing with a stochastic future or an uncertain future, there's one thing, you take an action, but simultaneously you hedge. And if I was countries around Europe, I'd be hedging like crazy. I want to just say one more thing. I've got to thank Amy for putting on such an amazing conference and inviting me. I feel very honored.
Yeah.
Thank you.